Okay, let's start looking at carbonyls. This is chapter 20. This, my friends, is a long chapter. We're going to be in here for a while. Okay, so let's just dive right in. The main stuff about carbonyls. Note we are going to find out there are generally two classes of compounds when we deal with carbonyls. Your aldehydes and ketones. Note these have carbon-carbon bonds or carbon-hydrogen bonds. And carbon-carbon and carbon-hydrogen bonds are fairly strong bonds. The next class, the other class, is what we call RCOZ compounds, where you have your R group, your normal methyls, ethyls, and alkyl groups, carbonyl, RCO, and then you've got it bonded to an electronegative group like OH, Cl, OR, nitrogen. So we've got the RC double bond O, same as aldehydes and ketones. However, we've got an electronegative group also attached to that carbonyl carbon. And what we're going to find out is aldehydes and ketones tend to do different reactions than RCOZs do. Also note, all of them have a carbonyl carbon, which is trigonal planar. Partial positive charge on the carbon, partial negative on the oxygen, sp2 hybridized. Carbonyls are uncrowded because it's a planar molecule, which means that carbon that has positive charge can be attacked from the top side, nothing in the way, or attacked from the bottom side. Okay, so the first thing to look at is let's look at nucleophiles attacking these guys. And we have to break them into the aldehydes and ketones versus RCOZ. We'll start with aldehydes and ketones. Aldehydes and ketones undergo nucleophilic addition. When you have a nucleophile, you get nucleophilic addition. Because the carbon R bond, the carbon-carbon bond is strong, the carbon-hydrogen bond is strong, they are not going to break. So a nucleophile, a negatively charged beast, is going to attack the carbonyl carbon. The pi bond of the double bond will break. And that will give us R. Note this arrow from the two electrons to the carbon means that we've now got this nucleophile attached to this carbon. We've got that H. Note, you'll see this a lot from now on, H parentheses or R prime, meaning we're dealing with a aldehyde if it's an H or a ketone. Ketone would work just the same. Okay. And so I just put the H there because I'm getting tired of writing parentheses or R prime the whole time. But this could be another alkyl group. Nucleophile attached. The two groups are still on the carbon. This oxygen is now negatively charged. If we add water, we can do a protonation reaction. Negative oxygen attaches the hydrogen here, and we get an alcohol and OH minus. Note, this is a two-step process where the nucleophile attacks, and then we have to somehow protonate this guy. And we usually use water, and so we tend to call this aqueous workup. So the main reaction was we needed that nucleophile to attack, and this is kind of like the side reaction, the aqueous workup. You have to add water to finish the job. All right, two-step reaction here. Note, aldehydes are more reactive than ketones towards nucleophilic addition, because there's less steric hindrance. A hydrogen is less sterically hindered than an alkyl group. And recall from previous chapters, alkyl groups are slightly electron donating. So the two R groups, each one of them will donate a little bit of electron density to this carbon, making that carbon slightly less positively charged. If it has less positive charge, then it's not as attractive to a negative nucleophile. Negative things like positive things, very negative things like very positive things. The more positive the carbon is, the more a negative thing is attracted to it. Good old Coulomb's law. If you've got alkyl groups on here, they're both electron donating. The carbonyl carbon is a little bit less positive, which means it's a little less attractive to the nucleophile. So two R groups stabilize the carbonyl positive charge a little bit better. Aldehydes only have one R group on there and a hydrogen, so aldehydes are more reactive. The carbonyl carbon's a little bit more positive. All right, now, while aldehydes and ketones, when they deal with nucleophiles, do nucleophilic addition, RCOZ molecules do nucleophilic acyl substitution. Put that little acyl in there just to make it sound special. It's really just nucleophilic substitution. They introduce substitution reactions, not addition reactions. And it works like this. If you have an RCOZ compound, the nucleophile will attack that carbonyl carbon, negative likes positive. The pi bond will break, but then the pi bond reforms and kicks off Z negative. So you get your carbonyl back. And question, why didn't we just write it that the nucleophile attacks the carbonyl carbon and Z just leaves? Wouldn't that give us the same answer as this over here? Nucleophile attacks carbonyl carbon, Z leaves would give us this. We don't write it that way because that's not actually how it happens. Something to get into your head. Every time a nucleophile attacks a carbonyl carbon, the pi bond breaks. Pi bonds are weaker than sigma bonds. Pi bonds break easier. So the pi bond always breaks. And then after the pi bond breaks and the offspring becomes a negative charge, it says, oh, you know what I'd like to do? I'd like to reform that pi bond and kick off Z. And so that's what it does. Always, 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 always. Nucleophile attacks carbonyl carbon, pi bond breaks. Pi bond reforms, Z gets kicked off. That's how nucleophilic acyl substitution occurs. Okay. But if we're doing substitution reactions, recall from chapter 7, you have to have good leaving groups, right? Chloride is a good leaving group. NH2 minus is a strong base. It's a poor leaving group, which means when we look at our RCOZ compounds, we're going to find some are more reactive. This acid chloride here is very reactive because chloride is a very good leaving group. It's a very weak base. Hydroxide is a strong base. Alkoxides are strong bases. They do not leave as readily. NH2 minus is an extremely strong base, an extremely poor leaving group, which means if you had RC double bond O NH2 and amide, that's not going to be very reactive towards substitution because you got such a poor leaving group. All right. And we will be, throughout the rest of, or a lot of this semester, looking at examples of these substitution and these addition reactions. Addition with aldehydes and ketones, substitution with RCOZ. All right, but next we're going to look at redox reaction. Recall, oxidation increases number of CZ bonds. Usually the Z is going to be carbon, or the Z equals 0. What's this? Number of CZ bonds. Usually that there's no Z on there. There's no Z atoms to begin with, and we're going to put a Z on there, a more electronegative atom. Oxidation also decreases the number of carbon-hydrogen bonds. Reduction increases the number of carbon-hydrogen bonds or decreases the number of CZ bonds. And recall our scheme. In alcohol, we have carbon bonded to one oxygen. Aldehyde or ketone, we've got two bonds between the carbon and the oxygen. Carboxylic acid and esters, we've got three bonds between the carbonyl carbon and electronegative atoms. All right. Reduction of aldehydes and ketones, we've got two main reagents we can use, lithium aluminum hydride and sodium borohydride. It is much preferred to use sodium borohydride to run your reduction of aldehydes and ketones, usually with methanol as a solvent. It selectively reduces aldehydes and ketones to primary or secondary alcohols in the presence of most other functional groups. So sodium borohydride is a reducing agent that really wants to reduce aldehydes and ketones. If there's something else in there, a carboxylic acid, say, or a double bond, it will not reduce those if there's an aldehyde and ketone present. Lithium aluminum hydride is a sledgehammer. It is an extremely powerful reducing agent. It is not selective. Lithium aluminum hydride reduces whatever it can get a hold of, which makes it actually quite the dangerous reagent. If you get this on you, it will reduce you to something you do not want to be reduced to. Okay, so let's look at the example here. If you have a aldehyde right here, Add sodium borohydride, the double bond oxygen, we put an H on the carbon and H on the oxygen, H on the carbon, H on the oxygen, and we've reduced it to the alcohol. Note, it is reduction, we're adding hydrogen. We've added H2 across the double bond. One hydrogen on the carbon, one hydrogen on the oxygen. Across the double bond, we've added a H2 molecule using sodium borohydride. Lithium aluminum hydride, same thing. We'll add an H to the carbon, an H to the oxygen. We get an alcohol. All right. Aldehydes will give us primary alcohols. Ketones give us secondary alcohols. And the mechanism is nucleophilic addition because lithium aluminum hydride is H minus. The electrons of the hydride attack this carbonyl carbon, double bond breaks. Now this oxygen's like, well, these are carbon-carbon or carbon-hydrogen bonds. They're pretty strong, so this oxygen attacks the water molecule, and we get our alcohol. And this was lithium aluminum hydride. The same will work with sodium borohydride. Something to note, lithium aluminum hydride especially and sodium borohydride would much rather react with water. It's much easier to react with water than this carbonyl. So any water around is going to kill the reaction. So you have to make sure that you're under fairly anhydrous conditions when you do the reduction, when you add the hydrogen to the carbonyl, and then when that part is over, then you add the water. This is a two-step reaction. Add the sodium borohydride and methanol or the sodium borohydride or lithium aluminum hydride first. Add the water, do the aqueous workup second. All right. Another way of adding hydrogen across a double bond is catalytic hydrogenation. Just H2 palladium on carbon. And we found H2 iron and HCl, H2 and zinc will also work. But the standard is catalytic hydrogenation with H2 palladium on carbon. Note, this is going to assume, because we're dealing with carbonyls here, that there's no nitrobenzenes around, because recall, H2 palladium on carbon will reduce the nitro group to an NH2. All right. So, if you have this ketone, you can reduce it to the primary alcohol using H2 palladium on carbon. It's another way of adding it. The deal is, though, sodium borohydride is a heck of a lot cheaper, a heck of a lot easier, because palladium, sorry, expensive. Hydrogen gas, sorry, not fun to work with. Hindenburg. So it's much easier just to add sodium borohydride to get the reduction. However, this reduction will occur if you had H2 palladium on carbon in there. And now the interesting thing is, recall, as we mentioned just a bit earlier, that sodium borohydride selectively reduces aldehydes and ketones. That's what it wants to react with. Turns out H2 palladium on carbon selectively reduces double bonds and triple bonds if they are there. Which means, let's look at this. If we had this cyclohexenone, gotta love that, cyclohexenone. We've got the carbon-carbon double bond right here. We've got the carbon-oxygen double bond right here. Sodium borohydride reduces the carbonyl to the alcohol. If you started with the cyclohexenone and add H2 palladium on carbon, it preferentially will reduce the double bond and leave the ketone. Now, if you add H2 palladium on carbon and you reduce the double bond, but you keep on pumping in the H2 gas, if there's no more double bond to reduce, then the H2 will reduce the carbonyl to the OH. Which means starting with this molecule, we can decide, okay, do we want the double bond, the alkene, and the alcohol? Do we just want to keep the carbonyl? Or do we want to get rid of the double bond and get rid of the carbonyl to the alcohol? We can do it whichever way we want by monitoring our reagents. And at this point, everyone says, that's cool. That is awesome that we are controlling the reagents. We're not letting the reagents control us. But what about stereochemistry? That's always a concern, isn't it? Yes, here's the deal. Let's look at this molecule here. If you have CH3, CH2, C double bond O, CH3 here, this ketone, If you had sodium borohydride followed by water or lithium aluminum hydride followed by water, do the sodium borohydride. Don't get involved with this guy. He's dangerous. We will reduce this to an alcohol, and now we know this carbon has a methyl, an ethyl, a hydrogen, and a hydroxyl group. That carbon is a stereocenter now. It is a chiral carbon, which means since there were no chiral carbons here, this is not optically active. This is not optically active, but our product, we generated one chiral carbon, which means it has a non-superimposable mirror image. We must get the racemic mixture of these two. Every time you do reactions with carbonyl carbons such that that carbon now has 4 bonds coming from it, if they are all different, you generate a carbonyl carbon and you're going to get racemic mixtures. And that's a problem with these reactions, is you never want racemic mixtures. You almost always just want one of the products, one of the enantiomers. You're going to get a 50-50 mixture of both enantiomers, and then you're going to have to separate them. So, very quickly along comes Corey, Bakshi, and Shibata, and they generated their CBS reagents. By the way, Corey, Bakshi, Shibata get the Nobel Prize for their work in stereochemistry and doing this type of thing, trying to cheat the rule that if your products are not optically, or if your reactant is not optically active, then your products cannot be optically reactive, which means trying to get around the rule, if you generate a chiral carbon, you're going to get 2 enantiomers 50-50. And what they found is if they deal with these ketones, where you've got a benzene ring, a phenyl ring, carbonyl, and a ketone here, and I'm not going to worry, I'm not going to have big questions about CBS reagents on the exam. It's just something to know that if you start with the SCBS reagent, which is a chiral molecule, so what they've done to get around it is they're using chiral catalysts. They put in the S chiral catalyst, it'll put H minus from the front here to make one of the enantiomers. Use the RCBS reagent, it will bring on that hydrogen from the back to make the other enantiomer, and usually in really, really good concentrations. You will often find that if you had this molecule here and you had the SCBS reagent, that means a hydrogen comes in from the front, you will get 97% this isomer, only about 3% of the other enantiomer. And that's pretty impressive, and that gives you Nobel Prizes. All right. So that's pretty long. We're at 18 minutes. Let's end this video now, and then we're going to look at reduction of carbonyl compounds, or carboxylic acids and their derivatives. We're going to look at reducing RCOZs because we've got some fun to discuss.